यजत्राः स्थिरैरङ्गैस्तुष्टुवागुंसस्तनूभिः व्यशेम देवहितैयदायुः स्वस्ति न इन्द्रो वृद्धश्रवाः स्वस्ति नः पूषा विश्ववेदाः स्वस्ति नस्तार्क्ष्यो अरिष्टनेमिः स्वस्ति नो बृहस्पतिर्दधातु ॐ शान्ति शान्ति शान्तिः हरिः ॐ नमो ब्रह्मणे नमो अस्त्वग्नये नमः पृथिव्यै नम ओषधिभ्यः नमो वाचे नमो वाचस्पतये नमो विष्णवे बृहते करोमि ॐ शान्ति शान्ति शान्तिः हरिः ॐ असतो मा सद्गमय तमसो मा ज्योतिर्गमय मृत्योर्मा अमृतङ्गमय ॐ शान्ति शान्ति शान्तिः हरिः ॐ तत्सत् श्रीरामकृष्णार्पणमस्तु।
स्थापकाय च धर्मस्य सर्वधर्मस्वरूपिणे अवतारवरिष्ठाय रामकृष्णाय ते नमः. The whole of India was tense around 6 p.m. on 23rd August 2023 when the moon lander Vikram was to land on the surface of the moon in the crucial stage of Chandrayan 3 project of the Indian Space Research Organization, ISRO. After a few minutes, Vikram landed on the moon successfully, bringing cheer and joy not only to hundreds of scientists, engineers, and other personnel involved in this mission, but also to 1.25 billion Indians residing in India and other thousands living across the globe. It was a momentous occasion when India walked on the moon, heralding a new age of spectacular scientific achievement of the highly gifted Indian space scientist. Dear friends, we are here to celebrate the success of those scientists. We are here to honor them. We are here to learn from them. We are here to get inspired by them. So in the beginning, we are going to show some videos, exceptionally good videos, rare videos of the India landing on the moon. Please enjoy the video show. Thank you very much. Thank you very much.
Friends, we'll be showing you a brief glimpse of the landing of Chandrayan 3 on the moon mission and the making of it. Hope you will enjoy it.
The mission strategy of Chandrayan 3, from spacecraft injection to lunar orbit acquisition, is similar to Chandrayan 2. Propulsion module of Chandrayan 3 will carry lander module up to approximately 100 by 100 kilometers lunar polar orbit. Subsequently, lander module will get separated from propulsion module at 6 days before landing. The new onboard functional verification strategy is adopted to assess the health and functional characterization of landing sensors and propulsion system during these 6 days. Also, contingency communication link between lander module and Chandrayan 2 orbiter will be tested during this phase. All the above assessments are newly introduced in Chandrayan 3 for better characterization of critical systems before the actual powered descent starts. Day 6 is a buffer day. Powered descent starts at appropriate time on day 7. Before the start of powered descent phase, orbit determination activity will be continuously carried out by utilizing JPL, ESA, ISRO ground stations and orbit models. The accurate orbit determination estimation is very essential to determine precise initial conditions of lander-powered descent, which is one of the critical requirements to achieve safe and soft landing. Powered descent phase consists of 4 sub-phases, namely rough braking phase (RB), attitude hold phase (AH), fine braking phase (FB), terminal descent phase (TD), which is similar like Chandrayan 2 except for phase durations and target milestones. All sensor electronics will be in on condition prior to start of powered descent phase. However, absolute sensors will be operated at the respective phases as per the powered descent. The filter will be updated by absolute sensors, and the filter, which in turn will be updating the inertial and local navigation and the speed intervals as per the descent. Inertial sensor will always be in closed loop with guidance and control throughout the descent phase. Rough braking phase will start from a nominal altitude of approximately 30 kilometers with orbital velocity of approximately 1.68 km per second. A second-order polynomial closed-loop guidance law with pure inertial navigation is planned for this phase. No absolute sensor will be taken in loop during this phase. All 4 liquid engines will be operated at higher throttling level to reduce the horizontal velocity. Maximum downrange will be covered during this phase. Total duration of this phase will be of this phase. Lander will be at an altitude of 7.4 kilometers and its attitude will have 50-degree pitch angle with respect to vertical. The expected vertical velocity and horizontal velocity at the end of rough braking is 61 meter per second.
I will try to play slightly from behind because the voiceover, I understand you could not hear properly, so that you will understand the various phases that it has undergone.
At 6 days before landing. The new onboard functional verification strategy is adopted to assess the health and functional characterization of landing sensors and propulsion system during these 6 days. Also, contingency communication link between lander module and Chandrayan 2 orbiter will be tested during this phase. All the above assessments are newly introduced in Chandrayan 3 for better characterization of critical systems before the actual powered descent starts. Day 6 is a buffer day. Powered descent starts at appropriate time on day 7. Before the start of powered descent phase, orbit determination activity will be continuously carried out by utilizing JPL, ESA, ISRO ground stations and orbit modules. The accurate orbit determination estimation is very essential to determine precise initial conditions of lander-powered descent, which is one of the critical requirements to achieve safe and soft landing. Powered descent phase consists of 4 sub-phases, namely rough braking phase (RB), attitude hold phase (AH), fine braking phase (FB), terminal descent phase (TD), which is similar like Chandrayan 2 except for phase durations and target milestones. All sensor electronics will be in on condition prior to start of powered descent phase. However, absolute sensors will be operated at the respective phases as per the powered descent plan. The filter will be updated by absolute sensors, and the filter which in turn will be updating the inertial and local navigation at discrete intervals as per the descent plan. Inertial sensor will always be in closed loop with guidance and control throughout the descent phase. Rough braking phase will start from a nominal altitude of approximately 30 kilometers with orbital velocity of approximately 1.68 km per second. A second-order polynomial closed-loop guidance law with pure inertial navigation is planned for this phase. No absolute sensor will be taken in loop during this phase. All 4 liquid engines will be operated at higher throttling level to reduce the horizontal velocity. Maximum downrange will be covered during this phase. Total duration of this phase will be approximately 690 seconds, with a downrange of 713.5 kilometers. At the end of this phase, lander will be at an altitude of 7.4 kilometers and its attitude will have 50-degree pitch angle with respect to vertical. The expected vertical velocity and horizontal velocity at the end of rough braking is 61 meter per second and 358 meter per second respectively. At this moment, lander will be approximately 32 kilometers away from targeted landing site. Also, a constant check on vertical velocity will start from an altitude of 18 km onwards. In case of any dispersion beyond design limits, emergency landing will be triggered, which will invoke salvage guidance algorithm. Rough braking phase is followed by attitude hold phase, which is planned for a nominal duration of 10 seconds. Guidance law in this phase runs in open loop with pure inertial navigation to decouple attitude control from guidance and maintains a constant 50-degree pitch angle throughout the phase for both altimeters to look at nadir direction. Both altimeters, Kara and Lhasa, will be operated in this phase and altitude data will be taken into navigation filter. These sensors update will be enabled to the filter from 10 km altitude. At the end of this phase, navigation filter will update inertial navigation with altitude information. Altitude of lander is expected to be approximately 6.88 kilometers. Lander module will be 28.5 kilometers away from planned landing site. Guidance bound check will be done to see if given landing site is reachable or not. In case if it is reachable, lander will be targeted to the designated landing site. If not reachable, then real-time retargeting will be invoked to reach neighboring landing site. If the guidance states are much beyond the real-time retargeting limits, emergency landing will be invoked. During this process, if there is a valid altimeter update, then the lander will be targeted to an altitude of 800 meters. And in case there is no valid altimeter update from both the sensors, the targeted altitude will be increased to 1300 meter to cater for inertial navigation dispersion. A third-order Polynomial closed-loop guidance law is planned for this phase, with LIRAP-propagated inertial navigation. In case if there was no valid altimeter update in the previous phase, then one more update from filter LASA altimeter data will be planned at 35 seconds from start of this phase. LDV will provide information about 3-axis velocity with respect to moon surface from an altitude of 2.5 kilometers and below. Navigation filter will run in background and will get update from LDV. Inertial velocity will get corrected by update from filter to navigation at time to go of 39 seconds. At the end of this phase, lander module will be vertically above targeted landing site at an altitude of 800 or 1300 meter from local surface with 0 velocities. Emergency landing logic will continuously monitor vertical velocity and salvage guidance will be invoked if dispersions goes beyond limit. Inertial navigation will be terminated and local navigation will be initiated to perform relative navigation with respect to local surface. Terminal descent will start from an altitude of 800 meters or 1300 meters. If all the requirements are met, 2 opposite liquid engines 1 and 3 will be shut off at the start of this phase. Lander module will hover above landing site for 12 seconds using PV guidance. LDV and CARA will be taken in loop to update height and velocity information to navigation filter. LASA and LHVC will operate in background as a redundant sensor to CARA and LDV. At the end of hovering, navigation filter will update navigation. Subsequently, lander module will descend vertically up to 150 meter local altitude using third-order polynomial guidance law. During this phase, the local navigation states will be updated at discrete intervals by filter. At 150 meter, lander module will again hover for 22 seconds using PV guidance. CARA and LDV will be taken in loop to update height and velocity information to navigation filter. During this time, hazard detection camera LHDAC operation will be carried out to find safest location within 150 meter downrange for landing. The first preference will be given to the location just below lander, if it is safe. In this case, lander module will vertically descend to 10 meter above landing site. In case LHDAC finds different safe location, lander module will be retargeted above new landing site at an altitude of 60 meters with 0 velocity. In retargeting phase, no absolute sensor update will be taken into the loop. From 60 meter, lander module will vertically descend to 10 meter altitude using third-order polynomial guidance. During this phase, the local navigation states will be updated at discrete intervals by filter. LDV will stop updating below 30 meter and CARA will stop updating below 10 meter altitude. Filter will not be updating using any absolute sensor below 10 meters altitude. LIRAP propagated inertial navigation will be used below 10 meter altitude. From 10 meter downwards, lander module will approach the lunar surface with constant velocity of 1 meter per second. At touchdown, contacts with sensors in lander leg will sense the touchdown and based on it, NGC will command to shut off all thrusters and engines. Throughout the descent phase, lander real-time telemetry data will be available in S-band. Apart from this, lander is also equipped with an X-band high-speed data transmission system, which will continuously send near real-time imaging, critical aux data and telemetry parameters to the Earth ground station. After landing, rover will roll down from lander and carry out scientific experiments with rover mobility on the lunar surface for continuously 1 lunar day.
the presentation.
Dear friends, the heroes of the day are coming now. Open money. So please welcome with standing ovation, please. Every one of you stand up and give a round of applause to them. They are now the national heroes. Give a long ovation until they come and occupy the seats. The national heroes, our great scientist, Srimati Nigar Shahaji and Dr. P. Veera Muthuvel. We welcome, hearty welcome, sir. Now we are commencing the stage program. Swami Vivekananda always cherished the hope that India, as in the past, would make great strides in the scientific field. It is he who gave the idea of starting an organization dedicated to scientific research to Jamshedji Tata, who made a reality in the Forum of Indian Institute of Science, Bengaluru. Swamiji also interacted with some of the great scientific minds like Nikola Tesla and exchanged his intuitive knowledge about physical sciences. Ramakrishna Mission, from its inception, has been promoting the study of science along with the traditional knowledge and shaped several bright students into talented scientists. It is a proud moment for the Ramakrishna Mission to state that 4 of the former students of the Ramakrishna Mission are directly involved in the Chandrayaan-3 space mission. Sir, we are very proud of you, sir. We are very proud of you, madam. Now, Swami Mangalatanandaji will welcome the dignitaries.
Good morning and my loving namaskars to all. As you know already, today is ISRO Scientist Felicitation ceremony, along with an interactive session with the students by these scientists. To give just an introduction, Chandrayan-3 landing on the South Pole of the Moon was not just a triumph of scientists at ISRO a few days back, but a tradition in history of science that looks at exploration as a spiritual path. It is a story of battle against all odds and challenges. It was a story of how the Indian scientists, despite the odds, did something that will remain the most remarkable achievement in the history of human science effort. India can do it was the feeling that the lakhs of Indian spectators were left with, who are watching the historic moments live streamed, glued to their seats and eyes wide open when the lander touched down on the south pole of the moon. The story of Chandrayan-3 is a story of grit, espionage, betrayal versus courage and commitment, and above all, our brilliance. The mission Chandrayan, along with Aditya, success Prime Minister Modi calls of Jai Vignan, Jai Anusandhan, also brings to mind the struggles of the past of India's leading scientific minds to rekindle India's scientific tradition and mindset amidst colonial subjugation. the inspiration imparted to, just now our Maharaj spoke about it, Jamshedji Tata by Swami Vivekananda to set up a research institute of science in India is well known. It would not be out of place to mention here Nikola Tesla, one of the greatest scientists the world has seen, used to attend Swamiji's lectures in the USA and interacted with him. Hiram Maxim, the founder of the first automated machine gun, rarely missed Swamiji's talks in Chicago. Also, William James, the father of American psychology, German scientist Hermann, and Indian scientist J.C. Bose considered Vivekananda as their guide. This happened because Swamiji believed in pursuing truth, whatever may be the mode. Swamiji stressed the need for science education and scientific temper in India based on its ancient spirit. Continuing now with this idea, Jamshedji Tata, I have to give a brief introduction to Swamiji's and his importance in the science field of India and its building nation. Jamshedji Tata had requested Swami Vivekananda to take the lead in rousing public opinion in his favor. The Swami had to decline any involvement because of his preoccupation with building the monastery at Belur and because of indifferent health. But he indicated his full support behind the idea. Tata, along with his assistant Burjorji Patsha, writes author Kunal Ghosh in his Unsung Genius, A Life of Jagdish Chandra Bose, then met Lord Curzon, the Viceroy of India, in 1898 for discussing the proposal of starting a science institute in India. Curzon was his own summarily shot down the project on the specious ground that Indians were incapable of achieving real mastery in science. Curzon had the gumption to say this, knowing well of Jagdish Chandra Bose's recognition in Europe as an eminent scientist 3 years prior to this and of his first scientific tour to these European countries 2 years before this meeting took place. In fact, William Ramsay, who would go on to win the Nobel Prize in Chemistry in 1904, had derisively told Bose, "You are an exception. One swallow does not make a summer." Ramsay, then a dominant mind in the Western scientific world, who had much say in shaping colonial scientific policy, exuded a race prejudice and sided with Curzon in his rejection of the scheme. A deeply disappointed Jamshedji sent his sister and Pacha to meet Swami Vivekananda in 1899 in Calcutta to discuss the issue. Though being Indian, we don't much of these things at all. They sought help from the Swami and it was given in full measure. How? Prabuddha Bharata, the flagship English newsletter of the Ramakrishna Mission, which was already being widely acclaimed, then published from Madras, carried an appeal by Swami Vivekananda himself in support of Jamshedji's decision to defy Lord Curzon's will and to go ahead with the project to promote, nurture and rekindle India's scientific talent. This all happened in 1898. In his appeal, Swami Vivekananda spoke of not being aware of if any project at once so opportune and so far-reaching in its beneficent effects was ever mooted in India as that of the Postgraduate Research University of the Tata. It was a scheme, the Swami argued, which grasps the vital point of weakness in our national well-being with a clearness of vision and tightness of grip, the masterliness of which is only equal by the munificence of the gift with which it ushered to the public. Vivekananda's appeal concluded with the following words, forcefully articulated in the print in defiance of the attitude of the colonial masters. We repeat, no idea more potent for the good of the whole nation has seen the light of the day in modern India. Let the whole nation, therefore, forgetful of class or sect or interest, join in making it a big success. Swami Vivekananda's appeal in support of Indian science thus generated waves across the Indian intelligentsia and the thinking public. Following this, Sister Nivedita, one of the most active advocate of India's scientific prowess, a pillar who stood by and supported the scientific endeavors and struggles of the likes of Jagdish Chandra Bose, wrote several articles in the Statesman supporting the Tata project and wrote to many British educationists. There were also others who bolstered the campaign. The points and counterpoints continued with forceful advocacy for the scheme and for allowing India's scientific spirit the scope for emerging. This phase was symbolic and marks the beginning of India's struggle in modern times to achieve parity, independence, equity, and power in the quest for science and for knowledge. The national education movement that soon followed this episode gave further boost to the demand and aspiration. In the sense, with Chandrayan 3's landing in the south pole of the moon, a region which has never been frequented before, another phase of that struggle has achieved successful and victorious completion. On the occasion of 125 years of Ramakrishna Mission celebrating its inception, today we are honored to felicitate some of the scientists who have contributed immensely in sending this Chandrayan 3 and Aditya L1. To grace the occasion, today we have revered Swami Nityastanji Maharaj, who is the Adhyaksha of Ramakrishna Math, Bangalore. On behalf of all who are present here, I extend a warm welcome to Swamiji. Representing ISRO for Aditya L1, we have Srimati Nigar Shaji, the Project Director, Aditya L1. On behalf of all, I extend a warm welcome to her. We have one more scientist by name Dr. P. Veeramuthuvel, Project Director, Chandrayan 3. On behalf of Ramakrishna Math and all present here, I extend a warm welcome to Sri. And also we have Mr. B.S. Jagdish Babu, Manager, Acoustic and Vibration Test Facilities, to interact and to we get felicitated. On behalf of all, I extend a warm welcome to Sri Jagdish also. And I welcome the Swamis and Brahmacharis of Ramakrishna Math who are present here, along with many of the ex-scientists of ISRO who was here, who are all well-wishers of Ramakrishna Math, Bangalore. Jagdish is there, and I forgot about Sudarshan, Sridhar Murthy, Lakshmi Shah. Yes. So they are all ex-servicemen to our ISRO. They are all here to see this function. I extend a warm welcome to all of you. Warm welcome to the teachers and faculties and the pillar of the program, my dear young students. Welcome to this occasion. With this, I conclude and request Dr. Vishwanath, who is our devotee and well-wisher of Ramakrishna Math, alumni of IIC and IIT, to introduce each one of the scientists. Thank you.
Pranams to revered Swamiji. Good morning to all the delegates, guests, and my friends. It's indeed maybe I'll have to extend the welcome address by one line. Srimati Kalpana, who is not here right now, is likely to join any time after finishing her one important meeting at the ISRO Center. And now it is my proud responsibility or occasion, whatever it is you may call it, to introduce our guests. Background you already heard, so I will give their personal educational background, what they have been doing, what they achieved, etc. I concentrate mainly on the background, what they are about in this presentation, whereas in citation we will go to the specifics of their achievements for this today's felicitation purpose. First to start with is Srimati Nigar Shaji received her bachelor's degree in electronics and communication engineering from Tirunelveli Government Engineering College, Madurai. She completed her master's in electronics and communication in Birla Institute of Technology, Ranchi. Joined the UR Center of Satellite Center in 1987, a long stay. Shahji has worked in several fields including communications, satellite design, control systems, and to list out, there are many things which I may run for even paras and pages. I will only say that she was instrumental in developing high-frequency payload data reception of all ISRO remote sensing spacecraft. She also headed the Satellite Telemetry Center at ISRO, Bangalore. Shahji also is the program director of Lower Earth Orbit Planetary Systems. She is responsible for developing the all ISRO developed low Earth orbiting spacecraft and interplanetary missions. She is presently the project director for Aditya L1 spacecraft, which all of us know on September 2nd. Yes. So with this she continues to contribute to the Space Department in various responsibilities. And with this, maybe a small introduction. She has several research papers to her credit, which I don't attempt to list them here for the lack of time. I know all of you are waiting to listen to them about Chandrayan and Aditya. I move on to Dr. P. Veeramuthu Vel. Dr. Veeramuthu Vel got his PhD in mechanical engineering from IIT Madras, worked in ISRO previously as Associate Professor Director for Chandrayan 2 mission, Project Director for the 3 ISRO nano-satellite missions, Project Manager cum Deputy Project Director, Systems for Indian Mini Satellite, etc. So many other satellites listed over here. Veeramuthu currently works as Project Director Chandrayan 3. Maybe you would have seen him on TV on August 23rd, next to Director Dr. Somnath. And he was very successful in smooth landing of Chandrayan lander and lunar surface close to South Pole, and it was his project direction and leadership that India got that success. And India became the 4th country to achieve a soft landing on the moon and the first to land near its South Pole. Following the successful landing, all predefined objectives were also accomplished. This is a very important statement too when we get into the discussion. Predefined objectives have been satisfied. Maybe you will have some questions toward the end. He is presently heading the study team for Mars landing mission. Maybe I would has more than 20 years of experience in spacecraft systems and management, project management at ISRO. I think this would suffice. One could get more and more details in the ISRO website. Now, I come to introduce our own person. In the sense, there is a very interesting group of training center here in Bangalore, Ramakrishna Mutt, what is called Balaka Sangha, Vivekananda Balaka Sangha. Many boys have been trained for the last more than 55 years, if I remember correctly. He was one of the old member of the Balaka Sangha. We are proud to have him here. A very shy person to say, but somehow we have brought him here onto the dais. I give a very brief background of Jagdish Babu. He joined ISRO in 1985 as a senior engineer specializing in instrumentation and testing. He is currently the manager of acoustics and vibration test facilities and heads the dynamic testing team. I remember myself when I first visited ISRO in 1971 or 72, if I am not wrong, in the Tech Center, Pune. Aryabhata's model was there, And when I came to 72 in NAL for a small 2 weeks training kind of thing, I saw the same being there in the test bed, vibration test bed in 72. And of course, history has grown very fast. He was responsible for setting up 1,500 cubic meters reverberation chamber, one of the fantastic acoustic test facility. In addition to 29-ton, maybe 6-axis shaker facility, 3-axis, okay. He is a member of various spacecraft teams as a project manager, deputy project director, etc. And he was responsible and contributed to Chandrayan 1. And he has got the Technology Excellence Award instituted by ISRO. And very interesting part of Jagdish Babu, as I said, being a Balak Sangha member, his passion for propagating science of satellites and rockets in general space science in Kannada. He has written 2 books and he has given several talks, both in workshops and conferences in Kannada. That way he is contributing immensely for the education of the local boys or students in Karnataka. With this, perhaps I could complete my by introducing the guests. Anyway, since Srimati Kalpana is about to join any time, I am worried about our introduction also is in order. Srimati Kalpana joined ISRO as a radar engineer at SDA Sriharikota in 1999 and served in the role for 5 years. She then moved on over to UR Satellite Center, Bangalore in 2005, a satellite system engineer. Some of her key responsibilities over the years include project manager, electrical systems for mini satellites and Youth Start, deputy project director for Saral satellite, and associate project director, electrical systems for Chandrayan 2, and recently associate project director, spacecraft for Chandrayan 3. Perhaps with this small introduction, I am closing the introduction of the guest for the day. Thank you very much. We'll continue with the rest of things.
Now it is time to felicitate the honorable scientists now. First I call upon Srimati Nigar Shahji, Project Director, Aditya L1. Madam, please occupy. And a small memento from the Ramakrishna Math, Bangalore. Please give a round of applause. Now we are very glad to invite Dr. P. Veera Muthuvel, Project Director, Chandrayan 3. Now we are giving the citation of Srimati K. Kalpana also to P. Veera Muthuvel. Memento. Then we are very much honored to felicitate our own VBS, Vivekananda Balak Sangha alumni, Shri B.S. Jagadish, Manager, Acoustic and Vibration Test Facility, ISRO Bangalore. Now we are going to start a very interesting part of this program, and presentation and response from the scientist, and there would be presentation also. So we would request all the guests to move below and sit there. Yeah, no first. It will take few moments. Now I would request Srimati Nijar Shaji, Project Director, Aditya L1, to give her presentation to the students. Welcome, madam.
ಲೈಟ್ ಆಫ್ ಮಾಡ್ತಾರೆ. ಇದು ಯಾವ ಮಾಡಲ್ ಇದೆ? ಇದು ಆಟೋಮೆಟಿಕ್ ಮಾಡಲ್ ಇದೆಯಾ?
ಗೊತ್ತಿಲ್ಲ ನಿಮ್ಮ ಪಿ ಸಿಯಲ್ಲಿ ಹೆಂಗಿದೆ ಅಂತ. ಸ್ಕ್ರೀನ್ ಸೇಲ್ಸ್ ಇದೆಯಾ? ಈಗ ಕಾಣ್ತಾ ಇದೆ. ಸ್ಲೈಡ್ ಶೋ
ಆಗಿದೆ.
ಸ್ಲೈಡ್ ಶೋ ಎಲ್ಲ ಇದು ಇಲ್ಲೇ ಬರ್ತಾ ಇದೆ.
ಇಲ್ಲಾಂದರೆ ಹೀಗೆ ಮಾಡೋಣ. ಝೂಮ್ ಇನ್ ಆ್ಯಂಡ್ ಪ್ಲೇ.
ಸ್ಲೈಡ್ ಶೋನೇ ಮಾಡಿ.
ಸ್ಲೈಡ್ ಶೋ ಹೊರಟೋಗ್ತಾ ಇದೆ. ಇಸ್ ಗೋಯಿಂಗ್ ಆಟೋಮೆಟಿಕ್ ಟೈಮ್ಡ್ ಸ್ಲೈಡ್ ಶೋ.
ಇಲ್ಲ, ವಿ ವಿಲ್ ಗೋ ಟು ಸ್ಲೈಡ್ ಶೋ. ನೋ ಶೋ. ಇದಕ್ಕೆ ಹೋಗ್ತದೆ.
ಟೈಮ್ಡ್ ಸ್ಲೈಡ್ ಶೋ.
ಇಲ್ಲ, ಬಟ್ ಇಟ್ ಈಸ್ ನಾಟ್ ಗೆಟಿಂಗ್ ಡಿಸ್ಪ್ಲೇಡ್ ಹಿಯರ್. Yeah. Good morning, all my dear students and all my ex-colleagues, senior colleagues who are our mentors here. Very good morning. And just I like to give you a just overview of the Aditya L1 mission. Later we can have an interactive session and you can have your questions so that we can clarify well. Yeah. First and foremost, why we want, you all will be having the same question, that why we wanted to have this mission. And it's mainly, as you know, we are living on earth because of sun, and it is very well necessary to learn more about the sun. And as you think, sun is not very calm and quiet. It's always very turbulent, and we should better understand the sun. And one more reason is, as compared to yesterday years, we have lot of spacecrafts in the space, and we have to, because sun is not, as I told, it was not quite calm, so it will be unleashing lot of charged particles, ions, electrons, and that will be coming and hitting. Even the earth is hit by those particles and ionized. It's called solar wind. But we are protected by our magnetic field of the earth. But even then, it tried to pierce through the magnetic field. That's why you might have read, that is Northern Aurora lights in the Norway. Northern Aurora, it's a tourism well developed there. So you can, if you go there, you can see the dance of the solar wind particles. That's called auroras. And so, if it is very strong, and the solar wind is, if it is going to be very strong, and we have, in addition to the solar wind from the sun, we have solar flares and also coronal mass ejection. And we don't know really the intensity of those things, and the intensity varies over time, and sometimes it will be harsh and sometimes it will be a less intense one. So once if it is very harsh, and if it hits our spacecraft, which we have almost now more than 50 spacecrafts in space India is having, and it can hit and even pierce through the magnetic field protection. And sometimes it's there is an event happened in 18th century that it was even disturbed our power lines in the Northern America side. So to protect our assets in space, we should know much more about the space, the weather conditions, space weather. It's called space weather, how we have, and the earth weather. In the earth we now have a very, very better models, and we are able to predict when the rain comes, when the storm comes. So similar way, we should have a better understanding of the space weather, that is the sun activities on the interplanetary space. So that we should be able to predict it well, and so that we can have a warning, so that we can protect our space assets. And these are all the two major goals by which this mission is being planned, and all over the world, the space weather is an upcoming subject, and every country is having their own space weather predictions and these spacecrafts for observing this. So this is the main scope of the project, and as you know, it's launched in September 2nd, and it is now, we finished our Earthbands, and it is traveling towards L1, and it will be by January 1st week, it will be inserted into a halo orbit around L1. And so, and apart from this, Sun also has a very important aspect we called coronal heating. That is, when you see, the center of the Sun, the photosphere, it's at 1000 or 2000 degrees centigrade. But as per your thermodynamic law, as the heat, the fusion continues and heat flows, it should, the temperature should reduce. But if you see the coronal temperature, it is of the million degrees centigrade, 1 to 2 million degrees centigrade. Still, there are various theories floating, and still it is not very conclusive and why and how this coronal heating is happened. And like this, lot of why coronal mass ejection is happening, why the solar spots, and why we have 11-year sunspot cycle, and how the sunspots are increasing, decreasing. All those studies also will be related to this. It's a very vast subject which is called the heliophysics, and a lot of people are working on heliophysics presently. So this is the basic scope of the project. Oh, sorry. Yeah, this is the some of the major science outcomes, because Aditya L1 is having 7 instruments for observing. One is for observing solar wind. It's a nice suite of instrument which can observe all the major events of the Sun: solar wind, solar flare, and coronal mass ejection. So these are all some of the major science outcomes. I'm not elaborating, and during the interactive session we can have more insight into this. So this mission also has a lot of uniqueness, and the instruments built. There are many instruments which are first time. That's one, we have a UV instrument. So that is first time it is trying to resolve the solar disk in the UV band, and also we are going still closer to the Sun. That what we call is the corona. Corona you can see only from Earth, you can see only when the Sun eclipse happens. You might have seen the photographs that the center disk will be covered by the Earth, and you will be the faint outer, that is called the corona. So there we are going closer to the limb of the corona. Till now, what they have achieved is 1.1 R0. That's called R0 is the radius of the Sun. So 1.1 R0. So we are trying to go still closer. 1.08, 1.05 is what we are planning, and also have lot of intelligence built on board to have the better data download from the space. And these are all some of the missions already what the other nations have. We have few more missions at the L1 point. I'll just come to the L1 later. These are all just to give you an idea how much spacecrafts are on the space for the weather studies as well as the astronomy, and even for the outer Voyager, outer Milky Way. It has gone beyond the Milky Way, our galaxy, and like that lot of spacecrafts are being, even separately for the heliophysics itself, a dozen of spacecrafts is already in the space. Okay, coming to where we are going to have this Aditya L1 spacecraft. It's going to be at L1 point. It's called the Lagrangian point because it's, these points are invented by a scientist named Lagrangian. So any two large mass bodies, if you take in this case it is Sun and Earth, there is 5 points where the gravitational pull of both the bodies will cancel each other and will be a very small force existing, and which will be able to, we are able to have a spacecraft whose centripetal force can be compensated by the small force on that point. So that this is the 5 points exist, and in this each point has its own advantage. If you see here, this L1 has an advantage. We can have a continuous observation of the Sun. That is the advantage of the L1 point. This L1 point rotates along with the Earth around the Sun. And a spacecraft around that will have an advantage, always 24/7 it will be able to observe the sun. Similarly, if you take L2, this point has an advantage. If you want to observe deep space without much interference from the sun, then that L2 point is the most apt one. Similar to that, the L3, it is okay, it is you can observe it, but still now nobody has tried this L3. L1, L2 has been tried. You might have heard recently the James Webb telescope that is being put at this L2 point. And L4, L5 or they call it stable points where the lot of asteroids got into, that's most of the asteroid belts will remain normally in an L4, L5 points. If you take other planets also, Sun, Jupiter and all. Okay, so here we are planning to have a halo orbit around this, and our spacecraft will be continuously monitoring the sun 24/7. This is the advantage of this point, and this orbit also, it's a quite large orbit, and its orbital period is of the order of 6 months, 178 days. And it is at 15 lakh kilometers from Earth, and it will take almost 125 days for the spacecraft to reach that point and get inserted. And presently, Aditya L1 is on its way in the heliocentric phase, on its way to the L1, and it will be inserted by January 1st week. Okay. Anyway, I have explained why we have chosen the halo orbit. And we have the 7 payloads. Just I will cover the 7 payloads. The first one is the coronagraph. Coronagraph, it's an optical payload, and it does the imaging. So its main purpose is to study the coronal heating as well as the coronal mass ejection, how it is happening. And also it is tried to map the magnetic field of the coronal, sun coronal magnetic field. And the next payload what we have is, it is observing the solar disk in the UV region. That is also, it is also an optical payload, it images the center of the disk. And we have the next 2 payloads, we have an in situ payload that will be sampling and observing the direction, velocity of the ionized electrons, protons, which is emanating from the sun. And the another 2 X-ray payloads we have, it's also a spectrometer payload, which also will be having, will be studying about the solar flares. And finally, we have a magnetometer. If you see the interplanetary magnetofield, it's very faint. It is of the order of 10 to 15 nanotesla. And see, our Earth magnetic field, if you see, it's 40,000 nanotesla. So we have in this spacecraft, we have a boom, because the spacecraft magnetic field should not affect this, because if the spacecraft are much larger than the 10 to 15 nanotesla. So not to affect, we have put these payloads on a boom of 6 meters, so that the magnetic effect of the spacecraft will be very less, and it will be able to measure the very faint magnetic field of 10 to 15. So this is just explaining all the instruments. This instrument, it's a very quite complex instrument of weighing of the order of 180 kgs, and it was built in collaboration with the Indian Institute of Astrophysics. They have designed, integrated and tested, and it is finally integrated with the spacecraft. These are all some of the subsystems and the testings what we have done, I have indicated. And this is the next payload. This is also, it developed in collaboration with IUCA Pune. It is also a scientific institution of the country. And these are all the subsystems. This, if you want more insight into these instruments, we'll have it during the interactive session. This is developed by our ISRO's PRL laboratory. This is also a particle in situ particle analyzer, developed by SPL Trivandrum. This is the 2 solar X-ray spectrometers, mainly for the study of the solar flares, are developed by URSC, and magnetometer is also developed by LEOS. And this is just to show how the payloads are accommodated. Here all the payloads always wanted to view the sun, so it's been accommodated accordingly in the spacecraft. All the payloads are accommodated facing the sun, and this is the magnetometer which I was talking about, a 6-meter boom, which will get deployed after reaching L1, and the magnetometers will be measuring the magnetic field. These are all the different views of the accommodation. And coming to the bus system, we have the spacecraft to support these payload systems and also to maintain the spacecraft in the halo orbit. See, we need to have a lot of other subsystems like propulsion. The propulsion system is essential for it to, the engines has to burn to reach it after the launch to the 15 lakh kilometer. We need the propulsion system and the control system to keep it and the sensors. So all those systems are built to support the payload systems and have very good science output which will help the heliophysicists of the country also to the world. Okay, thank you, and we'll have an interactive session.
Thank you very much. Thank you very much. Thank you very much, Nijar Shahji Madam. Now I request Dr. P. Veeramuthubel, Project Director, Chandrayan 3, to give his presentation. Welcome, sir.
Presentation. Yeah. There it will come correctly. Okay.
Namaskaram Swamiji, Namaskaram to all. Thank you for inviting me to be part of this event, and I am really privileged and honored to be here, and also all the distinguished invitees who are present here, my Namaskaram, and students, my greetings to all. So let us move on to Chandrayan 3. I will cover the very basic points like what are the challenges going to moon, what are the challenges in landing onto the moon, and what are the scientific instruments we had in Chandrayan 3, and how many countries have gone, what are the challenges in conducting the test in Earth simulating the moon's environment, and also some of the pictures what Chandrayan 3 has given post landing, and some of the videos I have. So with this, at the end of it, we can have an interactive session. Coming to the lunar landings, as you all aware that 3 countries have landed successfully who have mastered the safe and soft landing technology. One is US. They had Ranger in the beginning and followed by Surveyor. Ranger was having many failures, and then they moved on to the next series of satellites called Surveyor, and then Apollo became a crewed mission. They carried the man onto the moon, and the previous Soviet Union, they had a series of lunar landers, and China has also had various landers, that is Chang'e. They started with an orbiting mission, Chang'e 1 and 2, and then 3rd and 4th mission and subsequent missions they had a lander. And our India had a Chandrayan mission. Chandrayan 1 was an orbiting mission, Chandrayan 2 was a landing mission, and Chandrayan 3 is also a landing and roving mission. And these are the locations in which the lander has landed. So as you can see, our Chandrayan 3 is near to the South Pole, where we landed at around 69.9 degree latitude towards south, and 32.3 degree east is the landing site coordinate. So the previous missions all were concentrated towards the equator, and we were the first country to go near to the South Pole. There are many unsuccessful attempts before the first successful landing, even for US and Russia. US have attempted 3 failures were there before they successfully landed the first mission, and USSR also they had 11 failures before the successful landing, and India too had 1 failure in Chandrayan 2. Even though the objective of Chandrayan 2 has many objectives like orbiting mission and the operation of the scientific instruments, that is remote sensing operations, Those were successful, even though the designed mission life of Chandrayaan 2 orbiter was 1 year, but it's still working. It's more than 4 years over, and orbiter is a very big success. But however, the landing we could not do in Chandrayaan 2. That's why the Chandrayaan 3 has come. And also the recent attempts which had failures, one is Bearsheet, that is from Israel, and Akuta R1 mission, that also from Japanese, and Luna 25, even though Luna had many failures in the beginning, but they also mastered the technology, but still they could not have a successful landing of Luna 25 with lot of new technologies they have gone into, they have implemented in Luna 25, but unfortunately they could not land, and their site and our site was very close by. Just 2 days before our mission, they could not successfully land. So coming to the differences between the moon and earth. As you all know, the moon gravity is 1/6 of earth's gravity, that is 1.62 meter per second square, and the diameter is also, you can see it is very less compared to earth diameter, and the mass is also very less. The most important thing is the lunar day. We have 12 hours of day and 12 hours of night, whereas in moon we have 1 lunar day is equivalent to 14 earth days. Similar way, 1 lunar night is also equivalent to 14 earth days. That's how the rotation period of moon is 28 days. And the escape velocity, this is very important. If you have to go to another planet, you require a velocity of 11.2 km per second. You have to throw an object with a velocity of 11.2 km per second to escape from the Earth's sphere of influence, which is 9 lakh kilometers from the surface. Whereas for the moon, it is only 2.38 km per second, which means with the lesser energy, we can go to another planet. So that is also one of the important aspect, that moon, we can treat it as a gateway to go to another planet. And the surface temperature, it is very interesting. You can see the surface temperature of the earth, it's around 15 degrees centigrade average temperature, whereas the moon, it has a very extreme temperatures. Whenever the sun is there, it goes to as high as 120 degrees centigrade. When the sun is not there, we call it as a lunar night. During that time, it goes to minus 150 to minus 170 degrees centigrade, depends on the location. Because this kind of a harsh environment due to no atmosphere present in the moon. Whereas earth, as we are all protected with an atmosphere, there is a good amount of convective heat transfer. Whereas in moon, such a thing is not there. That's why it goes to very, very extreme temperatures, both in the day as well as in the night. And atmosphere, as I already told, we are having atmosphere. There is a deep vacuum in the moon. And also the important point is the earth to moon distance is 3.84 lakh kilometers, which is not constant, and earth to the sun, earth to the moon is ecliptic in nature. The orbit is ecliptic in nature. It varies from 3.72 lakh kilometer to 4 lakh kilometer, it varies. So our average is 3.84 lakh kilometers. So the reaching moon orbit itself is a big challenge. First thing is we have to have a velocity for the satellite, required velocity for the satellite. Then if launch vehicle is not having capability to directly injecting into the moon's orbit, we have to raise from our satellite our own propulsion system. We have to propel and we have to raise the orbit, bring the moon orbit closer to the satellite should be brought closer to the moon's orbit. Then we have another challenges in case if you are doing like that, we have to have a precise translunar injection. Once you leave the earth, when you capture the moon is having another attraction. Even though the moon is also influenced by the earth's gravity, but still an object when it goes near to the moon is really attracting that object, for which we have to reduce the velocity of the spacecraft. We have to fire in an opposite direction to capture the moon's orbit. That is another challenge for us. And both these challenges, TLI, that is translunar injection, and lunar orbit insertion, we have no second choice. We have to leave on the particular day, particular time, without much dispersions on the various systems present in the spacecraft. So that's a big challenge, that TLI and LOI. And considering all these things, we optimize the number of maneuvers, because we have so many Van Allen belts we should not be attracted, all these electronic components should not be attracted with so many Van Allen belts. So we have to arrive at a design in such a way that with the minimum exposure, we are going to the moon. As I told, there are various challenges. One is the launch phase challenge itself. Unlike other remote sensing spacecraft or any other communication satellite, we have an opportunity to launch any day. Whereas for the moon landing mission, we don't have that opportunity. Typically, we get twice in a year. It falls in Jan, February and July, August. So this puts us a constraint that we have to realize the spacecraft, we have to technically correct, and still we have to launch. So that puts a heavy constraint on the time schedule also. Similar way, when we carry the spacecraft also requires certain orbit and certain time of launch. So that puts a constraint on the various other injection parameters requirements from the launch vehicle, like argument of perigee and the inclination, orbit size. These are all the important parameters. So the first challenge is the launch phase challenge. The next is, as I already told, reaching the moon itself is a challenge because of the velocity in which it has to travel and the orbit size what is required. The third one is the most important thing is the braking phase. So now you are starting with the zero velocity, you are attaining nearly 11 km per second. When we capture the moon, it is around 2.4 km per second. Now you have to kill the velocity to nearly 0 meter per second for a safe landing. So which means the braking acceleration it becomes very vital. As I told, in the moon there is no atmosphere. So we cannot use any aero braking techniques. We have to necessarily have active control propulsion system. That is the only way out for us to kill the velocity. So that we call it as a braking acceleration. From the orbital velocity to nearly coming to the surface with the hit with the that leg capable velocity, that is near to 0 meter per second. I would call it as a near to 0 meter per second. So you are coming from an orbital velocity to 0 meter per second. We are primarily using the propulsion system. Then the third important thing is all these systems in this entire braking acceleration time has to work in unison. That is sensors, navigation, guidance, control, propulsion system, everything has to work in unison, and it has to take a real-time decision because the entire descent trajectory itself is about 19 minutes. In this 19 minutes, we have no ground intervention, only one-way communication. The spacecraft can communicate with us, we can see what is happening in the spacecraft, but we cannot build a logic that we will command the spacecraft because we have no much time. So every intelligence needs to be built in the lander to take a real-time decisions what happens. But whatever happens, we have to have a soft landing. That is what our goal finally. So towards that, we built a lot of an intelligence and the sensors requirement. The moon we don't have any GPS in moon. So there is no way we have position and velocity information in moon. The spacecraft determination, particularly the position and velocity, we have no ways to tell because no GPS is available. We have our own onboard sensors, which is a terrain relative navigation sensors kind of an instrument we had for us to tell where is the spacecraft and what is the velocity needed to kill, what is the required velocity to kill further. So all this information comes from the absolute sensors. And finally, we are going to an unknown terrain. We do not know exactly, even though we characterized, but we do not know exactly what is the surface conditions of the terrain. It's an unknown terrain. As I told in the beginning, this is the targeting landing coordinates. In order to go there, we have to avoid the obstacles. So how our car has got a ground clearance, similar way lander also has got a ground clearance. We can afford for about some boulder height, for some crater depth, that much only we can afford. If you have a large boulder and we happen to land on that boulder, we may successfully kill the velocity, but we may topple the lander. So such obstacle avoidance also capability needs to be built. Finally, the dust also needs to be handled. So even though the surface is very fluffy in nature, but we need to even take care of the dust also. These were the challenges for any lunar landing mission. And the most important thing is, how do we get a confidence before the launch? For which we have a series of tests. Those tests how to simulate in Earth's environment, but simulating the moon environment. That's a big challenge. As I told in the beginning, the Earth's gravity is different, moon's gravity is different. The second important thing is there is no atmosphere, whereas here atmosphere is there. Third one is the conditions of the temperatures and other things. So how do we simulate? For which we devised various tests to qualify the system. So unlike other spacecraft where we develop a system and we undergo lot of tests like a regular test, environmental test like thermovacuum test and the vibration test and so on. Whereas here we cannot depend only on that for the success of mission, for which we have to do a series of tests for characterizing thoroughly the sensors, as I told, the absolute sensors which provides altimeter, altitude information, velocity information and hazard detection information. Similar way, the propulsion system should behave what we want. So all these things needs to be characterized. And the mass is also, the gravity we cannot change, but what we can play with is only the mass. So we have to reduce the mass by 1/6. Our model should be having a 1/6 of mass. These were the challenges in conducting the test on Earth. We did a series of tests, which I will touch upon subsequently. And having told what has happened to Chandrayan 2, we should know that Chandrayan 2, what has happened. See, we all know that it lifted off on July 22nd, 2019, and we had a series of earthbound maneuvers, and finally we injected the spacecraft to a translunar injection, and we captured the lunar orbit, and we captured in an elliptical way. Finally we circularized, and then the orbiter and propulsion, that is orbiter and lander, got separated. Finally the lander had its descent phase. This is the phase, very crucial phase. As you can see, the red color is the curve which is expected, the trajectory, expected trajectory, whereas the dotted blue lines is what happened on that day. Now you can see here 30 km we started the braking acceleration, which I was telling, braking acceleration from orbital velocity you have to come to near 0 meter per second. So rough braking phase went normal. The next phase called camera coasting phase, where we started our we got a deviations from the propulsion system. So we have a propulsion system, we had 4 engines. Out of these 4 engines we have over performance from the thrust, which has resulted in few other things, like we were away from the nominal states at the start of fine braking phase, way beyond the expected target points. Because of that, the start of fine braking phase did not go well. It demanded an aggressive maneuver. During this process, the spacecraft has a tilt of around 360 degree, nearly 360 degree it had a tilt. In this process, we lost the altitude, we gained the velocity. At the time of touchdown, our residual velocity was around 50 meter per second in both vertical and horizontal direction, which means no lander leg is capable enough to withstand that type of load. Even our aircraft, you can see, it has to take off in a very less vibration manner. Similar way, it has to land with the very benign velocity conditions. Then only the landing gear mechanism itself will work. So our target is around 2 meter per second or less than 2 meter per second. So with the kind of residual velocity what we experienced during Chandrayan 2 is way beyond. It is 50 meter per second. That's why we had a crash landing. So we got the experience from the Chandrayan 2. So we should not, it should not go away. So we started this Chandrayan 3 with all the on-orbit experience is utilized to a greater extent. And then whatever the failures we saw in Chandrayan 2, we thoroughly simulated on ground. That root cause analysis we have done, and we come up with the corrective action what is required. The third important thing is, in addition to that, our ISRO culture is how to further improvise the system. So that is why we have a robustness in the lander. There are various robustness we built in both hardware and software. And as I told, the ground test is very important. You have made lot of changes. Even some of the tests we could not do in Chandrayan 2 because of various other limitations. So those things we want to overcome in Chandrayan 3. And then the fourth important thing is, before the power descent, that is the critical phase of 19 minutes, how to characterize the systems, like be it sensors, be it propulsion system or navigation system, how do we characterize it thoroughly so that before the power descent we have a confidence. These are the 5 major parameters we have kept in mind before, even during the configuration stage itself. This will lead to a safe and soft landing. So now coming to some of the robustness aspects, I will not dwell into greater detail. If you have more questions, maybe in an interactive session we will take up. But as I told, hardwares and softwares have been, the robustness lander has been made more robust. We have strengthened in various aspects. The right from navigation, guidance, control, the trajectory part, that is the descent trajectory part. Then we built the multiple mission paths. Like in Chandrayaan 2, we had two paths, basically nominal path and contingency path. Here, this time we have built so many paths. If this is not working, the other option it has to go. If altimeter is not working, what is the next option? If one engine is not working, what is the next alternate? Likewise, we foresee what are the failures can come. How do we address these failures? That was our objective. This has led us in devising many paths in the descent trajectory. But for our fortunate on that day, we had a nominal textbook landing. But we built so many paths, and we also improvised the lander leg touchstone capability. We also improvised the software, NGC software, and we built some of the redundancies where we did not have a redundancy in Chandrayaan 2 due to mass constraint and various other aspects. So this time we went with the full redundancy, and also overall system also we improvised. So how do we did? Even though the launch vehicle capability is the same, keeping the liftoff mass same, the orbiter is functioning well. Chandrayaan 2 orbiter is functioning well. Whatever the 7 state-of-art payloads were there, all these masses have been transferred to lander. That's why we call it as a propulsion module in Chandrayaan 3. The main job of propulsion module is to carry the lander to the final lunar orbit and detach, so that the lander will be on its own. But in addition to that, we had one scientific payload in propulsion module 2 as a value addition, whereas the lander has been made more robust by converting the orbiter mass to the lander mass. Nearly 270 kg we transferred from the orbiter mass to the lander mass. And coming to special tests, which I have already told, to simulate, to characterize thoroughly, we devised 3 tests. One is called integrated cold test, wherein we developed one scale down model of the lander, exact lander, where all the sensors like absolute sensors, which provides altitude information, velocity information, then hazard detection and avoidance sensor, the inertial sensor, along with that navigation algorithms. All these things we have carried in an helicopter. Previously we did in Chandrayaan 2 time, we did in aircraft. See, aircraft has got some limitations where we cannot do a hovering. In our descent trajectory, if you would have noticed during the landing time, if you would have witnessed, we would have come from 30 km to 800 meter. At 800 meter altitude point, we were hovering. Hovering means there is no velocity in both the direction. We are just compensating the mass into gravitational by an upward force. Simply we are stagnating. During that time, we are having set of activities like getting the inputs from the absolute sensors. Similar way, 800 meter to 150 meter, we were vertically descending down. At 150 meter, again we had a second hovering for about 24 seconds. Again, during that phase, we were operating this hazard detection and avoidance sensor to avoid the obstacles. So all these things we thoroughly simulated in an helicopter. We used helicopter as a platform. We created certain artificial lunars and craters in Chitradurga area, our own area. We flew these sensors and navigation systems in the helicopter. We had several sorties. Almost 3 to 4 months of tests we did, and we had so many issues in the beginning, and we corrected those issues. Again we requalified. Like that we did a number of tests. Second test is the integrated hot test, wherein we have brought propulsion system and guidance and control also in addition to sensors and navigation. Whatever ICT was only sensors and navigation, IHT we integrated other systems. But because we integrated other systems, the propulsion system also comes into effect. So it is an hazardous operation. We cannot do it in a helicopter, or we cannot do it in any other place what we desire. So we have to necessarily do with certain safety precautions. So we chosen Sriharikota as an area where we install the tower crane with the height of 74 meter, with the jib length of 74 meter. We again had a 1/6 of mass model. It's like a mini lander. And we did all this hovering, vertical descent, qualifying the guidance algorithm, qualifying the engines, sensors assessment under the engine firing condition, thoroughly characterizing the propulsion system. All these things we have done. Again a series of tests like dry run test, static test, dynamic test, closed loop test, like that. Then the third important test is a lander drop test. See, finally you have to land with the 4 lugs. These lugs, the main objective of these lugs is, at the time of touchdown, it has to absorb the impact energy. So it has to have a strength, it has to have a stability. When we touch, it should not topple. Under different conditions like horizontal velocity, the body may have an horizontal velocity, the surface may have a slopy surface, and you can have the CG also, the CG variations also. What I mean is a center of gravity. All these things may topple the module. So we have to have a lander leg which should absorb the energy, which should have a strength, which should have a stability. So for which we conducted a series of tests again. We created a lunar soil simulant test bed, which is simulating the lunar soil with both flat as well as 12-degree slopey terrain, and also with the different conditions of vertical velocity, horizontal velocity, as well as hard surface. Again, series of tests we did to qualify this. And third aspect, which I have already told, on-orbit testing, that is very vital. See, even though the systems are built, you have done a thorough testing, we have done a thorough simulations, but still the systems what we are taking it to, what we have launched, has not undergone the field test, because it's all flight, it is integrated in clean room, we cannot take it to field. So we need to characterize to an extent, at least before the critical power descent phase, whether these systems are characterized or not. So that is how we devised an improvised on-orbit characterization plan in Chandrayan 3. So these are, I am not just going into the detail. We have LVM3, we had 3 modules, propulsion module, lander, rover. We had totally 6 scientific instruments, 3 in lander, 2 in rover, 1 in propulsion module. The main objective is the safe and soft landing, rover roving on a moon surface, and conducting this surface experiments. These were the 3 objectives. All these 3 objectives are completely met in Chandrayan 3. And this is some of the mission profile which I already covered in Chandrayan 2. It's similar like Chandrayan 2, all these phases. Only even the power descent phase is similar like Chandrayan 2, but with so many mission paths. And finally, the prime landing site coordinate, as I already told, this is our coordinate, 69.3 degrees south and 32.3 degree east, and we had an alternate landing site. For example, 23rd August, if you would not have landed, we had a backup plan 3 days later of primary site. Eventually, because of the moon's rotation, you will actually come, the orbit, you will have a separation of orbital paths of 34 paths. You will come to west, from east to west. So we had a backup plan. It's not only for the landing, even for all other burns also we had a backup plan. Coming to the scientific instruments, just briefly I will tell, we had 3 lander payloads. Of course, one more payload from NASA was there, it's a passive instrument. Coming to CHASTE, it's a Chandra Surface Thermophysical Experiment. We had a probe which is got inserted into the lunar regolith. We had 100 mm of insertion into the lunar regolith. Every 10 mm we had a temperature sensor as well as heaters, which measures the temperatures as well as thermal conductivity of the lunar regolith over time for the entire one lunar day. Depends on the sun condition, depends on the sun elevation angle, the load varies. With respect to time, we were actually measuring this instrument. Second is the RAMBA, that is radio anatomy of moon-bound hypersensitive and ionosphere and atmosphere Langmuir probe. This was again deployed. This measures the near surface plasma experiment, both electron density and electron temperature. This was first of its kind. Globally, no one has conducted this experiment where it measures all this electron density and temperature over time again. And the third one is the seismic activity. We dropped the payload onto the surface of the moon. It measures the seismic activity, both natural as well as artificial. So any sort of, it's a high sensitive accelerometer is mounted here. So even a small kind of a meteorite impact, it can measure the vibration, and also the rover movement and various other deployments also it will capture. And fourth one is a passive instrument, which is basically a retroreflector array, which is mounted on the farthest point of the spacecraft, so that the orbiter, whatever the orbiters, lunar orbiters are there, if it is actually passing the laser, it will exactly tell the coordinates of the lander as well as the distance of the lander between the orbiter and lander. So this also was flown into the lander. Then coming to the rover payloads, we have got 2, even though the rover size and the mass is very, very small, and the mass is only 26 kg, which has inbuilt function of all the functions like a satellite. In addition to that, it has a mobility function also. So we had a drive mechanism, we had rocker bogie mechanism, we have differential mechanism, and in addition to that, we had 2 scientific payloads also. One operates in laser principle, other one is operates in X-ray fluorescent technique, and both measures the elemental composition of lunar soil. which has detected many parameters like iron, manganese, magnesium, titanium, sulfur, calcium, and even it has given oxide. There are various major rock forming elements and minor rock forming elements it has measured. And third, the another payload in the propulsion module is a shape, that is spectropolarimetry of habitable planet Earth. This also has a value addition we have put. This is basically for the future missions, like we know Earth is a habitable planet. Looking at from the moon's orbit, that is in the propulsion module, we know that what is the kind of detection it is going to give. But this payload will be used in the future, like Venus mission and all. We can find out Earth too. What is the exoplanet where similar kind of Earth, whether we can see from other planets. That was our idea. Though this is as like a experimental payload in that way. This test I have already covered. There is some of the glimpses you can see. This is how our spacecraft is integrated module, and these are the flight modules where propulsion module, rover, and the lander. And the right side is the integrated cold test module, where the view is inside the helicopter, and this is the integrated hot test during the engine firing condition. And this is the lunar soil simulant test bed. We had a 1/6 of model where we dropped at certain height to qualify our lander legs. You can play this video, a small video. Yes. Sound. It has come now.
The Chandrayan-3 spacecraft consists of a propulsion module and a lander module with a rover accommodated inside the lander. The propulsion module and the lander module are stacked together to form the integrated module. 6 modules were realized during Chandrayan-3 project life cycle, out of which 3 were flight modules and 3 were special test modules, namely the integrated cold test, integrated hot test, and lander leg drop test module.
The main function of propulsion module is to carry the lander module till lander separation. The propulsion module was made ready for further integration with lander module.
A 6-wheeled rover is accommodated inside the lander, which would be deployed after vibration test, thermo vacuum test, and mass property measurements were carried out. All tests associated to rover were successfully completed and the rover was made ready for further integration onto lander. After integration, detailed IST, sensor level alignment and EMI-EMC tests were also carried out before shipment to ASTE Bangalore. Realized at SDSC Shah for conducting the IHT. Craters and boulders simulating hazards during landing. A total of 20 tests were successfully conducted, which include 6 dry runs, 8 static tests, and 6 dynamic closed-loop tests. The lander leg drop tests were carried out to evaluate the energy absorption capability, strength and stability aspects of lander legs during touchdown. A new facility was realized at iSite with a test bed with flat and 12-degree inclined drop surface. Detailed tests were carried out at damper level, single leg level, simulator level, structure level for various touchdown velocities on flat and slope surface and on lunar soil simulant and hard surface. A total of 15 drop tests at simulator level and 2 drop tests at fluent structure level were conducted successfully. The objective of lander is to demonstrate safe and soft landing on lunar surface. Major elements of lander include sensors, after the completion of thermal elements in the rover compartment, the rover was assembled onto the ramp using 3 hold-ons. Detailed assembled mode IST was carried out, followed by mass property measurement, thermo vacuum test, solar panel assembly and illumination test, EMI-EMC test at CATF iSite. This was followed by 3 dynamic deployment of secondary rover ramp, primary ramp and rover rollout from lander and payload deployments such as insert and rumba, chased, and the lander was made ready for further activities. Once the lander module was ready, it was stacked over the propulsion module to form the integrated module. EMI-EMC, vibration tests, acoustic tests were carried out. Final finishing Chandrayan 3 space was made ready for shipment to spaceport at SDS. Acoustic tests were carried out. Final finishing activities such as MLI sealing, Chandrayan 3 spacecraft was made ready for shipment to spaceport at SDSC Shah.
Thank you. This making video was this. In fact, this voiceover by Kalpana. She has joined now. She will come during interactive session. And what you have seen is up to the spacecraft readiness, and it has been moved from our UR Rao Satellite Center to the spaceport, our Sriharikota. Further to that, some of the images I am going to show. This is how the spacecraft was made ready in Sriharikota, and finally it was transported to Sriharikota. Transported from the one of our preparation building to launch pad. And further, all you know that launch has taken place, and we had a series of maneuvers which I already covered. And this is the visuals this you would have seen during our live landing event. So one of the camera mounted in the lander, which was sending a picture for every 4 seconds in that entire 19 minutes. So portion of lander and portion of the lunar surface was also captured till landing. This is something we have as a part of our changes robustness. This also we have included in Chandrayan 3, and there is a expand transmission system which is continuously coming in that entire power descent phase. And this is very interesting. On the left side you can see just before the landing, our Chandrayan 2 orbiter, which I was referring, now more than 4 years over, still the mission is on. So before the landing, you can see on the left picture, and after the landing you can see here our lander landed, which is captured by our Chandrayan 2 orbiter high resolution camera, which is 0.32 meter resolution, which is globally, this is the best resolution available globally, and this was used for characterizing our landing site as well. A priori to launch itself, we have characterized this landing site, and the site is increased from earlier 0.5 kilometer by 0.5 kilometer to 4 kilometer by 2.4 kilometer. Such a big area we have identified in order to take a leverage from various dispersions in the lateral directions. And this is also very interesting. You would have seen this is an animation. This is how the ramp gets deployed upon landing, and once the ramp is deployed, the rover solar panel deploys, it establishes the communication, and rover rolls out from the ramp and it touches the lunar surface. This is an onboard camera visual. It is captured by our own lander imager, and the rover has come out and it has touched the lunar surface. As it was coming, it has also captured our Indian flag mounted on the rover. This is a very interesting picture. The lander sitting on a surface, upright condition, and taken by rover camera. So far you have seen lander camera taking a picture of rover. This is taken by the rover, which is 30 meters away from the lander. We had how our eyes are there, we had rover also got a navigation camera, which has taken, one of the navigation camera has taken a picture. This we were referring all the time, other lander when it was standing on the surface, like as I told, Changi missions, US missions, and Luna missions. Our own lander was there. This was very interesting, and it was an happiest moment for all of us. And this is again I was referring our Indian flag mounted on the rover backside. And these are the various visuals again. Along with that, there are some details, like the payload. As I told, one of the payload got inserted into the regolith, which is also captured here. It is a proof captured by our rover camera. And another payload which I was referring, the seismic activity, that also was dropped onto the surface. This is where the tilts are. And the another one payload which is not very clear in this, that also requires a deployment. Almost all the 3 payloads requires a deployment. It was towed during launch and landing, and post landing it was deployed. And this is again an interesting view where the lander, our Prime Minister has kept a name, Shiv Shakti point. This is where the landing point, and the rover has come out here and it has taken a turn, because rover has got multiple challenges. With the 26 kg of rover, we have to have, unlike lander, it is autonomous in nature, whereas here it is semi-autonomous. We have to take a picture, we have to avoid the obstacles and transmit these images to ground through lander, because rover does not communicate directly with the earth, it is always communicates via lander. So we have to do a path planning at ground, then decide which direction we have to move. Once we move from point A to point B, we have to operate the scientific payload, and one of the payload, again it's got a deployable element which needs a stowing before the next movement. Like that we had a multiple challenges. In this phase, the lander itself can cast a shadow because it's a moving shadow. The sun is not stagnant. In that 14 days it is moving in azimuth direction from east to north to west. Similar way, the elevation also it is varying. So it casts a long shadow. Even a small height, it casts a long shadow because of low elevation angle. So it traversed, rover has traversed to 101.4 meter in this one lunar day, which is it's a mammoth task, because even other landing missions took 120 meters with 6 months. We have operated continuously 24/7 in this one lunar day. It has given a plethora of science data. And this is one more very important thing. This is the HOP experiment. Just before our mission life, before end of our mission life, we again fired the engine where where the engines are used for landing. 2 engines are fired, and we have taken off from the position a slight elevated angle, elevated height, as well as dropping into a slightly a lateral position also was done. This also was a huge success, and you can see the visuals in the center how this was. These all are available in internet, our Twitter handle, so you can as well refer. And the left side picture, you can see how the dust is formed, how when engines are fired, how the dust is formed, and it took off only for 1 second, and it landed. So that we got, it's a precursor for our future sample return mission, as well as we got a new location for the lander payloads to be deployed. Again, the chaste was retracted during the HOP experiment, and again it is deployed back. It inserted into the lunar regolith again. We operated for 1 more day. Similar way ILSA, similar way Ramba payload also. And the mission outcome wise, there are many, still the scientific data has been collected a lot, and there are first cut analysis are available. So still it is an ongoing process. It takes much more time for getting into publications and so on. So it takes time, but there are various informations available in our ISRO Twitter handle. You can as well refer. So with this, I complete my presentation, and thank you very much. Madam and Kalpana can come, we can start the interactive session.
Hello. Thank you very much, sir, for your excellent presentation. Here is the good news. As Dr. P. Veeramuthuvel informed you, we are in the midst. Dr. Kalpana, the Associate Director of the Chandrayan 3 in our midst. We heartily welcome her. Madam, please come and occupy this. Here, madam. Here, madam. So we are very fortunate to have both Project Director Dr. P. Veeramuthuvel and also the Associated Project Director of Chandrayan 3 with us. So we are felicitating Srimati Kalpana.
Good afternoon, dear students and the organizing staff and also the organizers of Ramakrishna Matham. Thank you for inviting me and along with the project directors of Aditya and Chandrayan. You have all would have heard a very detailed presentation from the project director Chandrayan 3 himself. What more than that for you, because he has covered in detail starting from the concept to the completion of the project. So you would have got an insight into directly from the project director himself. So maybe I'll not be going into the technical portion of Chandrayan 3 because we both have worked together on this mission along with a big team who are, when I say big team, like the team of Chandrayan 3 itself, like they are across different centers of ISRO, all have put together and worked. Maybe only few points I can tell from Chandrayan 3 mission, what even as students you can derive from it. It's not just a technical mission. There are a lot of life lessons which have come out of it, and you can get a lot of inferences from this mission, because first thing is we took it as a challenge when we started Chandrayan 2 mission itself. It's not like any other satellite mission. It was totally new. So we had to work from the scratch during Chandrayan 2. So that itself it's like something innovative you have to try. For you also, it's not the routine things always always which you have to do, but trying something new is very, very essential. It is not going to be easy, definitely, because there is no one to tell you how to do. You have to learn from whatever material. That's what even we did from the internet, from the literature, whatever is available, we started learning and we put in our best effort. So first is innovation is a key in the science and technology. So all of you should not be hesitant at all about taking innovation, taking off and doing something new. And when you start something new, hard work is definitely very essential. So we have to put in our best efforts, and always we say do your best and God will do the rest. So that is what even we all did during Chandrayaan 2, and we put in our heart and soul, and we did try. And we, all of us as a team, we had worked together. But you all know what happened in Chandrayaan 2. We could not achieve that 100%. But again, this itself is a big lesson. Failure is not about not achieving. Failure is not trying something new only is the thing. So it should not define us. Always like failure should not be the definition for us. It should only teach us. So we as a team, we have learned from Chandrayaan 2 whatever has happened. We try to derive what we have achieved and what really went wrong. So that aspect we really focused, and again we started off fresh as a Chandrayaan 3 team. We wanted to do it again, start again and do it and achieve the goal. So what I would say is it's okay to fall or it's okay to fail. But what we learn from that and what we achieve is only very important. I think that is very essential for students also. You can really think it as a best example towards this. And next important thing what I would say is here when we are studying in a school or in a college, what defines us is how we perform in an exam. But next when you are going to work in an organization or anywhere, you have to work as a team. So Chandrayaan 3 I would tell is a best example for a team effort, because all of us as a team, we have worked together towards one common goal. So I think even you all, when you are working in a project, school level project or any college level project, you will be realizing this, because working together as a team is very, very important towards one common goal. So this is one more important thing what I would say is we have to work together as a team to achieve something very big. When a very big goal is defined, this team effort is also very much important. So when Chandrayaan 3 success, when we had seen, it was not a success of the scientific community, because the response what we have received is from every citizen of the country. It is like a national success. Every citizen of the country has owned this as their own success. So this is what has really made us happy. And when our chairman also told it, when he mentioned it is India is on the moon. So that is what has brought more happiness to all our Chandrayaan 3 team. So with this, I would like to wish all the students here all the best for their future and future endeavors. Thank you.
Now there is interactive session. The Speak to Space Scientist. I will invite all the 3 scientists to come on the dais. There will be 2 mics on the either side. And those who are interested to ask the question, please raise your hand. The mic will be passed on to you. But make the questions pointed, very short. Thank you very much. So the interactive section will start. Speak to Space Scientist. Those who want to ask the question, raise your hands. Please stand up. Please stand up. Yeah. Introduce yourself and then ask the question.
Good morning to all the scientists. I am Dr. Manjula from Adarsh Jain College. I am a professor there. My question is to Professor Nigar Sharji. Aditya L1, regarding Aditya L1. Now, after the success of this mission, some of the scientists are telling that all the environmental aspects, whether it is global warming, climate change, is not because of the human activities on the earth, it is because of the activities on the sun, especially solar wind or solar flares. How far this is correct, madam? Can you please answer?
No, Actually, global warming, effect of the sun on global warming is, as I have understood, it's not very much, because the solar wind and the activities, it's not mainly on the warming. It's only when it peers through the earth, it can disturb the ionosphere and thereby the communication or the electric that way. It's not, I don't think it contributes to the global warming.
Yes, here, front row.
Good afternoon to all. I'm Rekha from B&M Institute of Technology. We as researchers, we do understand scientific explorations and the probable outcomes. But to the common man of India, what is your answer about the success of Chandrayan 3?
To whom this answer is? A question is?
I think Muthuvelu sir.
See, immediately there is no usefulness to the common people for successfully landing, but the vision should be there. For example, when communication satellite was launched way back, when Arthur Clarke has told that 36,000 kilometers, when you put a spacecraft at 120 degree apart, it will cover globally. People have laughed at him, but now you see it is like our Bangalore no real estate. Yes. Our real estate is demanding. Similar way it is there. So our day in and day out life is on communication. Similar way, the moon, there are many objectives. Like first thing is, we have mastered the safe and soft landing technology. That is the first step. For us to study how this universe has formed, moon can be taken as a subject and study because it is undisturbed, where Earth is getting disturbed. Second is, the secondary objectives, if you see, there are many, like we can use moon as a gateway to launch other stations. Like if you find water, say there are, how this all evolved. In Chandrayan 1 has detected water molecules. So we have seen that permanently shadowed region, there are waters. If you know that, we can use that as a fuel for our launch station. Then because of these missions, there are many scientific temper as created across the country. Lot of scientific interest it is inculcated in the youth's mind. So this many people can come and join in the science. That is also another thing. There are various aspects to it, but definitely we can have a colonization. Like moon itself, no, we can go as a space tourism. In future, we can go and settle in moon. If you don't take a step now, there is an end for it. So science, it's there for us. It's only visionaries will do that.
Thank you, sir. Yeah, then I will. That small girl wants to question.
Pranama Swamiji and Namaste everyone. My name is Sharvi. I'm from 5th grade NPS PSK school, and my question is, I have heard people speaking about space station in the moon. What is that, and is it like airport or railway station?
We have future, maybe your next generation may see airport and railway station in moon also.
And if we go to moon, should we come back in 14 days as it will become night there?
No, see right now, our mission was limited by only the solar power generation. We did not have a nuclear resource. For example, the next missions, we should focus on the nuclear resources so that we have a long-term missions, like 1 year, 2 years on the surface. Even on the lunar temperature, as I was telling in my presentation, it will go to very low temperature during lunar night. Now, if you have some artificial power generation or even artificial radioisotope heating unit kind of instrument, it will keep the systems warmer. And even though the surface temperature is very low, but the spacecraft can be kept warmer. We did not have technology for Chandrayan 3, but in future it will be there. We will not leave you for only one lunar day. We will assure you that we will have a long-term mission. We don't have to run through in one lunar day.
Don't worry, you will be with a comfortable spacesuit. No worries.
Again, madam, we couldn't hear. Yes. Okay. From this side, anyone? Yeah. Yeah. Yeah.
My name is Mohit and I'm from BNM IT, Computer Science. I had one question on Aditya L1 mission. So since it's going closer to the sun and it does not have much electromagnetic field to protect it, how will the sensors and the spacecraft survive if there's a solar flare or some storm? So because it's more right near that region.
First of all, see, going near to the sun Earth is actually 150 million kilometer, and we are going 1.5. That is the 1% of the distance of the sun, and the temperature there is okay. It's controllable by our thermal system. And you asked about the radiation and how we are protected by how the spacecraft is, because the spacecraft, the components are tested for those radiations for the solar flares and the ultimate solar flares, and we have been using the components which can withstand such temperatures and such radiations. That's how it can survive.
From this side.
Namaste, I am Avyay from Baldwin International. My question is for Veeramuthu sir. Why is Chandrayan 3 not reawakening, and do we have any hope?
No, right now we don't have any hope. The lander and rover is no longer alive, because as I told, lunar night the temperature has seen very, very low temperature. With that condition, which is way beyond our storage limits. Like for example, our mobile, there is electronic systems. You have taken these systems to minus 175 degrees centigrade, and again bringing it back, where there are various challenges like components survivability, soldering joints, PCBs. There are many systems can go wrong. So the same question I was telling to the previous questioner, like there is no nuclear resources to keep it warmer during the lunar night. It simply it attained a thermal equilibrium. Whatever surface temperature was there, since we have not heated the lander also has experienced the same temperature. Because of that reason, there is no survivability, so we have no hopes.
This side? This side, anyone? Yeah. Please pass on.
Yes.
You raise your hand. Oh, yeah. And the last one. Last. Yeah. No, previous, that one. Yeah.
Hello sir, my name is Sriram, I am from NMIT. So my question is, how do you look on to improvise the lunar missions such as the LoopX mission with respect to the thermal conditions and on the South Pole?
Madam, you want to answer? No, lunar mission or LoopX mission?
Mission, sir. LoopX.
So LoopX, see, it is a future mission. It is a bigger size of lander, bigger size of rover, and it is targeted into the permanently shadowed region. Like there are theories that in the permanently shadowed region there are water molecules, frozen ice particles are there. So that is a big mission. Now you have seen in Chandrayan 3, the rover itself is a 26 kg mass, and lander is approximately 1750 kg. This much only we carried. And the scientific instruments, if you see 5 payloads, the total mass put together is 30 kg only. So we had a very limited payload experiments, whereas that is a very big mission. And because the capability from our launch vehicle also is limited to 4 tons, whereas the LoopX mission is targeted to use Japanese launch vehicle. So we are coming up with the bigger rover, bigger lander, bigger scientific explorations.
Thank you, sir.
From this side, anyone? Yeah. Here.
Namaste. My name is Supreeta. I'm from Dayanand Sagar College of Engineering. I'm a biotechnologist, and hence my question is, Is there any contribution of biologists in Chandrayaan 3 or Aditya L1?
No, we don't have any astrobiology payloads in both the missions.
Thank you.
Here.
Namaste. My name is Hemant. I run an academic research company. So my question is slightly into software part. This is for the team of both Chandrayaan and Lunar mission. Have you used any machine learning or artificial intelligence algorithms for decision making? Since, sir, you said it is rover is an autonomous decision making system. So have you used any algorithms?
Lander, as he would have already explained, is a totally autonomous landing sequence is adopted in landing itself. So there is a good amount of intelligence built in the lander software, because the decisions have to be taken based on the in situ measurements which is going on by the various systems like the sensors, various inertial sensors and absolute sensors, what he has told. So based on the measurement, lander is supposed to take an appropriate decision, like multi-mission paths have been built. So they are all in situ decisions which the lander software, whatever the software is built, the ALS software, what we call the autonomous landing sequencer, where the software, whatever is built, it has to take its own decisions. So good amount of intelligence has been built in lander. That is what we have strengthened, in fact, more strengthened compared to Chandrayaan 2. So this intelligence is what has made lander actually take proper decision and do the landing sequence. So compared to, coming to rover, it is not fully autonomous, it is semi-autonomous, because the measurements by the navigation cameras will be taken when the rover has to move from point A to point B. We have two navigation cameras left and right on the rover. This will be doing taking images, and these images will be sent down to Earth, and the digital elevation model will be derived from that, and looking at that appropriate point where it has to move will be selected on ground, and it will be uplinked, and then accordingly the rover will be doing mobility. So there it is semi-autonomous. That way good amount of autonomy has been built both in lander as well as rover.
This way?
Your question, no? Actually, a lot of autonomy is built in it, but we have not used any structured concepts of machine learning or artificial intelligence or the tools in it. We are yet to use that. We have lot of developments using the machine learning and AI. In future spacecrafts, it will be used.
Thank you.
That girl.
Good afternoon, everyone. I'm Khushbu, alumni from BNMIT. And my question is, what strategies or initiatives is ISRO planning in order to mitigate the space junk from the various student satellite programs to ensure sustainable future deployments? The space debris.
Are you talking about the space debris?
Yeah, exactly.
Yeah. No, as on earlier spacecrafts, there is not much mitigation that which is on the space. But now, spacefaring nations has come to an act, and they have brought out a resolution that each spacecraft, as soon as the life is over, it has to be brought back to the atmosphere and burn it up, so that it doesn't be roaming in the space. So that is being active, and many nations are trying to follow it. We are also trying to follow it, so that we will have extra fuel, so that as soon as the spacecraft is declared non-operational, it will be deboosted and it will be burned. That is one. Otherwise, for debris, we are pushing to the graveyard orbit. The communication spacecraft, we are pushing it to the above orbit, where it won't disturb the orbiting communication satellites. Otherwise, that a lot of research is going on in the debris catching and removal, but not very active till today.
To add it to that point, there are some techniques more than the propulsion system. We will be having that inflatable balloons, so that you can use the drag and then bring it to it. Then tether mechanism, there are many student satellites itself they are adopting. It is actually a part of it. Debris mitigation is a part of it, that many of the satellites, the foreign satellites of nano satellites, even the micro satellites are having. And another important thing, more than satellite, the spent stage rocket. That's going to be there in the space. So for that, we are having plans like our PSLV and all. We are converting that into a satellite. Already there are so many scientific payloads have been put. So we are utilizing that also.
Yeah.
Here.
Another question. Yeah. So what are the circumstances surrounding the Chandrayaan 3 which made you take a decision to put the Chandrayaan 3 into sleep mode? And what are the challenges you're facing in order to re-establish a signal?
What was your last word? What you told? Last? What were the challenges in putting in sleep mode, right?
No, what circumstances surrounding the decision to put the Chandrayaan 3 spacecraft to sleep mode, and what are the challenges you're facing now in order to re-establish the signal?
Okay. Sleep mode is, we know what is the mission life. It is 1 lunar day, and for this 1 lunar day is what the sun is going to be available. Okay. So sun presence is very much required. One is for the solar power generation. The total satellite needs power, and the temperature also has to be maintained to a conducive. So for this, sun presence is required, and this 14 days is the mission life. Towards the end of it, we are sure to know that there is not going to be power, and without power and also without the temperature maintenance is also going to be difficult. So we have to put it into an off condition. So gracefully we have to put all the systems off and bring it to a situation, at least we can be in a storage condition. See, as we told, there are very sensitive electronic components in the satellite. The avionics is comprising of all electronic components. So we have to put it at least in a storage condition, which is going to be the most, at least better conducive situation for the system to remain, than leaving it in a non-condition. Anyway, power is not there. So we are forced to put it in such a situation. Next is, we did build a scheme to attempt for any possible revival. That is called the sleep and wake up one logic we had built. But yeah, we know that the harsh environment is going to be very harsh with respect to temperature. A sleep and wake up logic we had built such that when we are again finishing the 14-day night life and coming back to again the dawn day where sun is going to be available, this power generation which is going to come has to power some of the wake up heaters which is spread across and bring it to a conducive temperature. The logic we had built, but the sustainability or the survivability of the electronic components in this 14-day night life was the most challenging part. So this is what is the main challenge. So the components surviving this harsh thermal environment is the challenge. But the scheme was still built to make an attempt and see whether really we can bring it back to life.
Thank you.
Yeah, here.
Hello.
Give him. Here, there is the yellow, the blue shirt, blue T-shirt. Oh, I have to, another one.
Good afternoon, everyone. I'm Nikhil from BNMIT. So as you told, from using a Chandrayaan mission, we discovered the existence of water on the moon. But even NASA says even they are the first to discover the existence of the moon, of water on the moon. So my question to you, sir, as what is a very important aspect, a very important component, who gets the credibility for this discovery, sir?
Who will get the credibility?
Credibility for the discovery of water on the moon.
See, in fact, the science missions, it cannot be done by only one country. In fact, the future is always the cooperation. Such a big missions like space stations or tourism or any other exploratory missions, it should be a partnership so that the cost comes down. So there is no question of credibility. Finally, we know the resources are there. That is what we need to tap on.
This side. Now let a student ask. Yeah, red dress.
Good afternoon. I'm Tanisha from VNMIT. And my question is, the rover is collecting samples, right? So is that going to be brought back to the Earth?
Rover is not collecting any samples. Rover is only detecting the rock forming elements like various. See, for example, I was telling in 2 payloads were there in rover. One is laser based payload that is works in one certain wavelength, 1000 to 1700 nanometer. It can detect certain minerals. It is only detecting and sending the data, not the sample. So in future we have to do those things.
No, that's just behind you.
Namaste everyone. Namaste to all the dignitaries on the dais. I am Gagan from BNMIT. My question is on Aditya L1. So basically now Aditya L1 is detecting the solar winds which are coming from the sun. So what's the prevention for the spacecrafts or satellites which are there on the already there on the orbits? What is the prevention part, and how will be the satellites protected from these solar winds?
No, this spacecraft is not built exactly to give a warning signal to the other spacecraft, because the space weather is an upcoming field and we don't have a very good model to predict exactly. So this data will be used to enhance the space weather models, but we have 3 in situ instruments. In that there is a trigger flag is kept when the electrons and ions which flows from the sun exceeds a threshold value that will be indicated by a flag, and that we will be detecting on the ground based on the intensities. We can, for the time is not automatically, there is nothing like as soon as the detection and giving a warning to the spacecrafts.
This right?
Another question. Recently there was a statement by ISRO chairman Somnath sir regarding the investment in the space agency. Like he was referring to Elon Musk, who has invested close together in US. So what is that which is inhibiting Indian investors to invest on the spacecraft and to see glorious, to get benefit out of it?
For that only the space reforms have been in place, and we are also starting up our startups, and because like Elon Musk, we don't have that much investors in our country to invest in space, and future it may happen.
This is the last question.
Good afternoon everyone. I'm Manasa from Ramya University. My question is, besides temperature and other sort of things, is there anything that ISRO is targeting particularly through your missions?
For temperatures means we
like,
didn't get the
because
question.
Chandrayan is in sleep mode right now. Okay. So besides temperature targeting, are there anything else which you are focusing on through these missions?
No, this is not only a temperature. There are 5 instruments which we talked about. Some were measuring temperature, some were measuring the lunar surface, near surface plasma experiment, some were measuring seismic activity, some were measuring the, as I told, detection of various chemical composition analyzer. Like that it is there. What all we are telling is temperature is not conducive for the second lunar day, for which we are telling that long-term survivability we will come up with the nuclear resources.
Thank you very much. Thank you very much. I know you, all of you, have questions. We are short of time now. Now the presidential address by revered Swami Nityastanandaji Maharaj, the President, Ramakrishna Math, Bangalore.
All the 3 dignitaries on the stage, Srimati Nigar Shaji, Dr. P. Veeramuttuvelu, and Srimati Kalpana K, and other dignitaries before me, and also Swamijis, revered Swamijis. Normally we think that India is very great spiritually. However, we know India was great in all other aspects of human endeavor. It was great culturally and great scientifically also. So much of contribution, especially in the field of mathematics, India has. So materially also very prosperous it was. And Swami Vivekananda describes the glory of India with such glowing terms. And also Swami Vivekananda envisioned a great future to India. India, according to Swami Vivekananda, he wished, his vision was India must be materially prosperous, scientifically highly advanced, culturally rich, morally strong, and spiritually bright. This is the vision of India Swami Vivekananda had. And we are very happy. And these ISRO scientists are trying to fulfill the dreams of Swami Vivekananda. It's a great step towards fulfilling the dream of Swami Vivekananda. So we are very happy about that. And we are so happy to invite them and honor them, facilitate them. And also we are very, very thankful to them for their achievement. And also we wish a great future glory to their endeavor. Very thank you so much. Thank you.
Now, the vote of thanks by Swami Anilyananda.
Dignitaries on dais, Revered Swami Nityasthanji Maharaj, Adhyaksha Ramakrishna Math Bengaluru, Revered Swami Atmavidanandaji Maharaj, Senior Monk Ramakrishna Math Bengaluru, esteemed guests, brother monks, brahmacharis, members of distinguished gathering, and my dear students, good afternoon. It is with immense pleasure and a profound sense of honor that I stand before you today to extend a heartfelt vote of thanks on this momentous occasion, Felicitation ceremony for Indian Space Research Organization scientists, organized by Ramakrishna Math, Basavangudi. We have gathered here to celebrate this creative work of the brilliant minds and relentless efforts of the scientists at the Indian Space Research Organization for their remarkable achievements with Chandrayan 3 and Aditya L1 missions. Today, as we applaud these remarkable achievements of Indian Space Research Organization, I would like to extend our heartfelt gratitude to the entire Indian Space Research Establishment, especially Dr. Veeramuthuvel, Project Director Chandrayan 3, and Srimati Kalpana ji, Associate Project Director Chandrayan 3, for your unwavering commitment to advancing scientific knowledge, pushing the boundaries of space exploration, and bringing pride to our nation knows no bounds. This is our small efforts to signify your achievements and imagine the young minds, especially students, to think beyond present capabilities. Thank you so much. In similar vein, I applaud the commendable work of Srimati Nigar Shaji, Project Director Aditya L1, that we pray Almighty to bring equal, if not more, glory for knowing the sun. These important milestones have carved a niche of India in space research among the other countries. Only few countries were able to achieve similar feat. We are very proud to say our country is one of them. We also acknowledge the critical support and encouragement from the Government of India, the Ministry of Space, who have been instrumental in enabling Indian Space Research Organization's ambitious endeavors and provided unwavering support. This has reposed faith in our scientists' ability, and their commitment to space research have been commendable. These missions are not just national milestones, they are significant contributions to the global scientific community. I must also take this opportunity to thank the families of Indian Space Research Organization scientists. Behind every successful scientist is a supportive and understanding family. Thank you so much for the sacrifices and encouragement have played an indispensable role in the achievements we are celebrating today. In conclusion, today's felicitation is not just about honoring achievements, but also about acknowledging the spirit of exploration and innovation that drives Indian Space Research Organization. I am sure your tireless efforts have ignited the imagination of countless young minds, especially students, and will continue to inspire next generations to dream big and reach for the stars. Once again, on behalf of everyone present here, I extend our heartfelt gratitude to the scientists and leaders of Indian Space Research Organization for their remarkable achievements with Chandrayan 3 and Aditya L1. Your dedication to the pursuit of knowledge is truly inspiration to us all, and we continue wish best of luck for more such future endeavors. I thank Sri Jagdish Babu for all his sincere efforts and also educating our students through his wonderful videos. Sri Jagdish is the Acoustic of Vibration Test Facilities Bureau for ISRO. And also I take the opportunity to thank Dr. Vishwanath, the former Deputy Director, NAL, for coordinating this event on the behalf of Ramakrishna Math, Bengaluru. Finally, we sincerely thank students, faculty, coordinators from different institutions, BNMIT, RV Group of Institutions, BIT, Sheshadripuram, Sindhi College, as well as MS Ramaiah Group of Institutions. Thank you so much. Let's continue to dream, explore, and achieve together for success for our beloved motherland, India. Thank you so much.
There is a small announcement. Please be seated before dignitaries leave. Please be seated. So there is a lunch prasad for every one of you in the open auditorium. We call it Sabhangana, Ramakrishna Sabhangana. So there will be lunch prasad for every one of you. Please partake the prasad. And our book stall is open now. You can buy books on Sri Ramakrishna, Swami Vivekananda and Sharda Devi, and also about the science and religion. So please take this opportunity. Please utilize this opportunity of buying books also. Once again, thank you very much. Thank you very much. Thank you.